Hey guys, I'm Vinay. In this video, we're going to talk briefly about some review of complex numbers and the complex plane and Euler's theorem and things like that. And then we're going to try to attempt to solve the number 3 on the worksheet. Okay? So let's briefly talk about kind of motivation for complex numbers. So what is a complex number? What's the point? Or what's kind of the problem that inspires complex numbers? So motivation. And the motivation is quite simple. There are some things that make sense to ask that simply aren't expressible with real numbers. So one thing we might ask is what number squared equals -1, right? We have some x squared equal to -1, then what's x, right? And if we think about properties of real numbers, you can kind of immediately see that there is no real number for which this is true, right? You know that if you square a negative number, you're going to get a positive number. And if you square a positive number, you'll definitely also get a positive number, right? And since every real number is either positive or negative, there can't be a real number that satisfies this. So to kind of answer this question of what number squared equals -1, we invented our own number, right? We just made a new number. And so we say that I is such a number. I is going to be equal to this number. That's the square root of -1. So I squared equals -1. Okay, so given this, a complex number is any number of the form a plus bi, where a and b are both real numbers. Okay, and so when we're dealing with a complex number, typically we call a the real part of the complex number, and b the imaginary part of the complex number, right? A kind of determines here's how much of this complex number is consisted of kind of a real component, and b tells you here's much of this complex number is consisting of its imaginary component. So when we try to visualize real numbers, we typically put them on the number line, right? We imagine this kind of line. Maybe we say, look, here's 0, here's 1, here's 2, here's 3, right? And we can even put other numbers on here, like here's 1/2, here's pi somewhere over here, right? So when we think of real numbers, we think about them on this number line. But when we think about complex numbers, this idea of a number line no longer makes as much sense. In some senses, we can think of complex numbers being two-dimensional, right? There's two components, a real part and an imaginary part. And so if we try to place a complex number on this number line, where would it even go, right? So when we visualize complex numbers, we're going to look at them on what we call the complex plane as opposed to just a number line. So the complex plane we're going to draw like this. It's just a simple Cartesian coordinate plane. And its two axes represent sort of the real and imaginary part of every number. So every complex number is going to appear as a point on this plane, right? And sort of its x-coordinate is going to determine how real it is, and its y-coordinate will determine how imaginary it is, right? So let's say this position is at 1, 2. We say that this point would denote 1 plus 2i, right? So given a plus bi, we just go a units to the right and then b units up to determine where it goes on the plane. So basically we have this coordinate system, right, where we say every complex number can be written as this coordinate, x comma y, which corresponds to the complex number x plus y times I. And so if you've looked at coordinate systems before, you know that there's actually kind of two ways about thinking of coordinates. And we're going to see in a second that it gives us two ways of kind of thinking about complex numbers as well, right? Cool. So we're saying that in the one sense, we can see a coordinate as being starting at the center, moving some amount left or right, and then some amount up, right? And that's sort of our x and our y. But another way to think about a coordinate system is to think of it as in polar coordinates. Or we go some degree out from the center and then rotate some amount. Like this. So instead of defining a point with sort of rightward position and upward position, we define our points with an angle and a magnitude. So we're going to call that angle theta and that magnitude r. Okay. So given this theta and this r, we want to think about how can we convert this to like an explicit expression for the complex number. Right? Here we said, here's an x and a y, and here's exactly how you translate to a complex number. Now we're saying here's a theta and an r, and we want to ask how do we translate that to a complex number directly. Okay? And so the way we're going to approach this is to try to establish a relationship between theta, r, x, and y, right? I think the easiest way to see this is to look at this as sort of forming a right triangle on the complex plane, right? Here's our x, here's our y, here's our r, and here's our theta. And you can see that this is a right triangle where the hypotenuse is r, and the sort of two legs of the triangle are x and y, and we have this angle theta. And so if we remember kind of trigonometric properties, we can relate theta and r to x and y. Okay, so let's think about cosine theta. In a right triangle, we can remember cosine is going to be equal to the adjacent side of the angle divided by the hypotenuse. So cosine of theta is going to be equal to x over r, which tells us that x will be equal to cosine theta times r. Nice. And similarly, let's think about now sine of theta. So sine of theta is going to be equal to the side opposite of the angle divided by the hypotenuse. So y over r. And this tells us that y equals r cosine theta. Cool. And so now we can sort of substitute into this expression our newfound values for x and y. And we're going to get something totally in terms of r and theta. So for x, we're going to plug in cosine theta times r. And for y, we're going to plug in, oh shit. Here it should say sine theta, right? Sine theta. And so for y, we're going to plug in r sine theta times I. Okay. And so factoring this out, we get that our new expression for our complex number is r cosine theta plus I sine theta. Okay. And if you remember Euler's theorem, you know that this expression within the parentheses has a nice form, somewhat mystifyingly actually. It's going to be equal to e to the power of I theta. So we won't quite prove why this is the case, but I recommend that you look at like the Wikipedia page for Euler's theorem to see why this is true. Okay. So kind of in total, what we get is that there's two expressions for our complex number. Right? So we can say that a complex number is either x plus y times I, where x and y denote its position on the complex plane in terms of like a rightward and upward shift, or we can define it as r times e to the theta times I, where r denotes the sort of distance from the center, and theta denotes a rotation in radians from the x-axis. Okay? And so these two expressions are equivalent, and we know that there's this relationship between x and y, where x equals cosine theta times r, and y equals r times sine theta. Okay, so that should be some basics on what complex numbers are and the two ways we can kind of represent them. We're going to shift gears slightly and talk about a related concept, roots of unity. Roots of unity. Okay. So we define the nth root of unity, nth roots of unity, to be all x such that x to the power of n equals 1. So, for example, the second roots of unity will be all the numbers that when squared are equal to 1. In this case, plus or minus 1, right? 1 squared equals 1, and negative 1 squared equals 1. So given an n, like, what's a general expression for the nth roots of unity? So if we want a general expression for the nth roots of unity, we have to kind of think about complex numbers, right? If you think about, say, the fourth roots of unity, we can see that they're not all going to be real numbers, right? In fact, there's 4 numbers it could be. X could be 1, -1, I, or negative I, right? 1 times 1 is 1, times 1 again is 1, times 1 again is 1. Or -1 times -1 is 1, times -1 is -1, times -1 again is 1. Similarly, if we look at I times I is -1, times I again gives us -I, and times I one more time gives us 1. And you can see the same thing will be true for -I. So -I times -I is 1, times -I is -I, and then times -I again is 1. So any of these numbers, when raised to the power of 4, is going to be 1. And not all of them are real. Okay. So we need to keep in mind that our solution space is going to include complex numbers. So to kind of solve this out, we're going to use that previous expression we derived for complex numbers before, where we said that any complex number can be written as r times e to the I theta. So we're going to write this out, and we're going to raise this to the power of n, and we're going to set this equal to 1. And so it helps to think about how can we express 1 in the same form. Well, let's look at the complex plane. If you think about the number 1 on the complex plane, it's going to appear somewhere along this x-axis at a distance 1 from the center and at an angle of 0, right, from the x-axis. So r is going to equal 1, theta is going to equal 0. But it's important to remember with with radians that an angle of 0 is also equal to any 0 plus any multiple of 2 pi, right? 0 plus 2 pi times k, where k is integral. So if there's multiple roots of unity, it's important to remember that this k can be a couple different values. So we know that r to the n times e to the I theta n is going to be equal to e to the power of I times 2 pi k plus 0, or just 2 pi k, where k is any integer. Okay? So now let's try to solve this out. So we want to come up with a general expression for the nth roots of unity. And so to do this, we're going to remember sort of that trick we learned with complex numbers earlier, where we can write it out in terms of e. So remember that any complex number can be written as e to the I theta. And what we want is that when this is raised to the power of n, it's going to equal. Okay. So in order to find a general expression for the complex roots of unity, we're going to remember the trick we learned earlier where we can write any complex number in terms of the power e. Okay. So to solve this out, we're going to use the trick we learned earlier where we write any complex number in terms of e. So specifically, remember that we can write any complex number in the form r times e to the I times theta. Right? And so we're going to raise this whole thing to the power of n, and we'll set this equal to 1. Okay. And so to sort of help, we need to think about how can we write 1 in a similar form? And to figure this out, let's look at the complex plane. So if we look at the complex plane, right, remember this is the imaginary axis. This is the real axis. We want to think about where the number 1 occurs. And so the number 1 is going to occur at a distance of 1 from the center and at an angle of 0, right? So r is going to equal 1, and theta will equal 0. But remember when we're working with radians that any angle theta is also equal to theta plus a multiple of 2 pi. So plus 2 pi times k, right? Where k is any integer. So we can see that r times e to the I theta to the power of n equals 1 times e to the power of I times 0 plus 2 pi k. Okay. So now we want to try to solve this out. So what can we say for sure about this complex number? Well, looking at this expression, we know its magnitude is going to be 1, right? So we can kind of ignore this r term here. Similarly, so that tells us that all we really need to think about are what are the possible angles or degrees of rotation. So looking at this, we can see that theta times n is going to be equal to 2 pi times k, where again, k is any integer, which tells us that theta equals 2 pi times k over n. And so if we go through all the possible integers k's, we'll see that this is cyclic. So let's look at a particular example. 2 pi times 1 over 4. Two pi times 2 over 4, and 2 pi times 3 over 4. But we said that k could be any integer, right? So what about 2 pi times 4 over 4, right? What about this guy? Shouldn't this also be one of the roots? Well, you can see that the 4 and the 4 here cancel, which just gives us 2 pi. And we know that 2 pi in radians is the same as 0 in radians. So we get a degree of redundancy here, right? These are the same. So if we only look at k0 through n minus 1, we're always going to get the first k roots of unity. And so to kind of double check our work here, let's plot these out on the plane and see if they are what we expect them to be, right? So let's look at the complex plane. At a magnitude of 1 and an angle of 0, we have the point 1, 0, right? So this tells us that 1 is the first of the 4th roots of unity. So that's this guy. At an angle of 2 pi over 4, that's here, we have the point 0, 1. On the complex plane, this corresponds to the number I. And as we said earlier, I is one of the 4th roots of unity. So this guy also makes sense. If we look at the point that occurs at angle pi here, that's going to be over here. And that's -1, 0, right? -1 is also something we said that was going to be a root of unity. So that works out. And last one is going to occur down here, right? 0, -1. And that's going to correspond to the value -I. Cool. So this tells us how to compute the roots of unity. Okay. At this point, we're about ready to tackle the worksheet. So let's start by looking at problem 3, part A, number 1. Okay, so this question asks us to express, let's write it out, express negative square root of 3 minus I in form P cos theta plus I sine theta for real P and theta. Okay, so if you think about what we've been working with so far, you can kind of see that all this is asking is to convert from the rectangular coordinates to the polar coordinates, right? So specifically, we have this expression one second, this should be plus I actually, negative root 3 plus I. And so if you think about that on the coordinate plane, we're looking at a point that's sort of negative root 3 this way and up 1 this way, right? Real part, imaginary part being 1. Okay? And we want to convert this guy to polar coordinates. So we're basically being asked, what's this angle? And what's this magnitude? Right? We want to find our r and our theta, or in this case, p and theta. Okay. And so if we remembered, we said that the x was always going to be equal to r times cosine of theta. And our y would always be equal to r times sine of theta. And what's nice here is that we know x and y, and we're just being asked to solve for r and theta. So x is going to be negative root 3, and y is going to be 1. Okay. And here we need to find theta and r. And a nice way to do this is to sort of divide the two expressions. If we divide the first equation by the second equation, we get that r times sine theta divided by r times cosine theta is going to equal to negative 1 by root 3. Or negative root 3 by 3. And if you look at this side of the equation, we can see that the r's will cancel, and sine over cosine is tangent. So we get that tangent of theta is going to equal negative root 3 by 3. And so if you remember some trig, we're going to get that theta equals 5 pi by 6. Now we can plug in our expression for theta back into this equation. So we get that 1 equals r times sine of 5 pi by 6. Sine of 5 pi by 6 is 1/2, which tells us that r equals 2. Great. So that tells us that r is 2 and theta is 5 pi by 6. So we can write out this as equivalent to 2 times cosine of 5 pi by 6 plus I sine of 5 pi by 6 to get our final answer. Okay, so now let's look at part 2. Here we're being asked to write out the third roots of unity. And what's nice is you can remember we found that explicit form for the third roots, for the nth roots of unity in general, and we can just plug in n equals 3 to find the third roots of unity. So remember we said the nth roots of unity would always be in the form e to the I pi times k over n, where k can be any integer. And specifically we found that if we looked at sort of all the integers, we found a pattern where after the k minus 1th integer, it would start to repeat. So specifically, we're going to look at k equal to 0 through k minus 1. That should be a 2 pi right there. Okay. So what we need to do is plug in 3 for n and our different values for k. So we have e to the 2 pi I times 1 times 0 by 3, e to the 2 pi I times 1 by 3, and e to the 2 pi I times 2 by 3, which gives us 4 pi I by 3. Okay, so these are our third roots of unity. Great. So now let's look at part 3. Okay, so for part 3, we're being asked to compute the sum of our values from part 2. So one thing you can notice is that there is kind of immediately obviously an advantage to having things in the form a plus bi, as opposed to r e to the I theta, right? You can see that if you have two numbers in the form a plus bi, it's a lot easier to see what their sum is, right? You just add the a's and then you add the b's. Conversely here, it's a lot more difficult to add the two numbers together, especially when theta is different. So in order to solve this part, we're going to convert our answers from part 2 to this form and then add them all together. Okay? So let's go through each of them, and we can kind of remember the following. X, as we said earlier, was always going to be equal to r cosine theta. And y was always going to be equal to r sine theta. So if we want to convert our values to this form, we just need to plug for r and theta, which is quite nice. So let's just go through these. For the first one, we can see that x is going to be equal to r times cosine of 0, or 1. Y is going to be equal to r equals to 1 times sine of 0, which is 0. Here, x is going to be equal to r times cosine of 2 pi by 3. Equals 1 times cosine of 2 pi by 3, which is equal to negative 1/2. And y equals 1 times sine of 2 pi by 3, which is equal to root 3 by 2. Okay, let's look over here. X equals cosine of 4 pi by 3, which is again equal to negative 1/2. And y is going to be equal to sine of 4 pi by 3, which is negative root 3 by 2. Okay, now all we have to do is pairwise or piecewise sum up the x's and then sum up all the y's, right? We can see that this number is 1 plus 0i. This number is negative 1/2 plus root 3 by 2 times I. And this number is negative 1/2 plus minus negative 1/2 minus root 3 by 2i. Okay, now let's see what happens when we sum them up. 1 plus negative 1/2 plus negative 1/2 is 0. And 0 plus root 3 by 2 plus negative root 3 by 2 is 0. So we can see that the sum of all our answers to part 2 is 0. And actually, you'll find that whenever you have sort of the nth roots of unity, if you sum them all together, you're always going to get 0. Okay, so finally, let's look at 3b. So in this question, we're being asked, what are the possible values for the square root of the square root of negative 1? In other words, what's negative 1 to the power of 1/4? Okay, so let's kind of approach this in the same way we tried to derive the nth roots of unity in the first place. So essentially we're being asked what number, when raised to the power of 4, equals negative 1. So if x to the 4th equals negative 1, then what's x? Okay. So let's start again by sort of representing x as a general complex number and representing negative 1 as a general complex number, and then trying to solve for the appropriate r's and thetas. So x as a general complex number is going to look like r times e to the I theta, whole thing to the power of 4. And negative 1 as a general complex number, well, let's look at the complex plane. On the complex plane, negative 1 occurs right here. We can see that that's at a magnitude of value 1 and at an angle of value pi. In other words, this is going to be 1 times e to the power of I pi will be negative 1. So r to the 4th times e to the I times theta equals 1 times e to the I theta. And remember again that even though this is an angle of pi, pi plus any multiple of 2 pi will be the same angle. So we really need to have plus 2 pi k, where k is integral. So looking at this, we can see that r is a real number when raised to the power of 4 that's equal to 1. So we can say that r is going to be plus or minus 1. And now we need to figure out what are the appropriate values for theta. So let's look at this exponent. Theta, we can say, is equal to pi plus 2 pi k. Or rather, theta to the 4 theta. Right? We raised this whole thing to the power of 4, which means that we need to multiply the two exponents. So really, this should be I times theta times 4. 4 theta, we say, equals 2 pi plus 2 pi k plus pi. That tells us that theta is going to be equal to, let's factor the top. So pi times 2k plus 1 over 4. So we know theta is going to look like something of this form. And so remember that with the roots of unity, we found that if we kept plugging in different values for k, we eventually got some periodicity. So we have to see how many different values are there for theta that are actually distinct angles. So let's try to list them all out. The first one is going to be pi times 1 over 4. The next one will be pi times 3 over 4. Pi times 4 times 5 over 4. And the last one will be pi times 7 over 4. Right? Because if we go up one more number, pi times 9 over 4, right? If you look at over here, pi times 9 over 4, you can see that this is the same thing as 2 pi plus pi over 4, right? And we know that this 2 pi is the same thing as adding 2 pi to an angle doesn't change anything. So this is the same thing as pi over 4, so it would be redundant. So we can see that the 4 thetas we have are pi by 4, 3 pi by 4, 5 pi by 4, and 7 pi by 4. But also notice over here we found that r could be either -1 or 1. So we have to ask ourselves kind of, does this matter? If r is a magnitude, does the positiveness or negativeness of this matter? Because if you imagine taking a number and sort of inverting its magnitude this way, all you're doing is providing a rotation by pi, right? If you look at an angle here of magnitude, say 5, and you quote unquote invert its magnitude to -5, that's the same thing as a 180 degree rotation, or a rotation by radian of pi, right? So we don't really care about the fact that r is like plus or minus 1. What we really care about is that its magnitude is 1. So we can think of r as just being equal to 1, and then that gives us our expression. So we have that it's e to the I pi by 4, e to the I times 3 pi by 4, e to the I times 5 pi by 4, and e to the I times 7 pi by 4, giving us our final answer.